Advanced Pre-Calculus, Chapter 8, Section 2, Vectors in the Coordinate Plane. I kind of have to apologize for Section 1. It was long, it was hard, and let me just start with this. Hopefully, you're in a little bit of a better mood now. And what I want to tell you about Section 2 is, you remember Section 1, all of that really hard. Make sure you draw things right. Make sure you do the angles right, law of cosines, law of sines, all that sort of stuff. For Section 2, when you're dealing in a coordinate plane, everything that you do will be right triangle trigonometry. That means you'll use sine, cosine, and tangent. You will not have to use the law of sines or the law of cosines in this section. You'll have to use it again a little bit later on in the chapter, but not really a lot, because we're going to be doing a lot of right angles. And when you start using things in the coordinate plane, a lot of things become easier. Okay, so in the last section, you did vector operations doing the scale drawings. And I said that I just, when I do the scale drawings, they are sketches. And what I really want to get you to is being able to use algebra and trigonometry rather than drawing things. And you still have to draw to understand, but they would just be sketches. So what we're going to do in this section is represent and operate vectors in a coordinate plane. And a coordinate plane would be the Cartesian coordinate system, x and y's. So we have an initial point, which is a point, a terminal point, which is a point, and then there are a couple of different ways to represent that in terms of x and y. So it makes it fairly simple. And there are two different ways to express the vectors that we're going to do in this section. There's going to be component form and linear combination. So look at this vocabulary. That's it. Compared to last section, pretty straightforward. So you've got a component form, which is a way to write a vector. Linear combination, another way to write a vector. And I skipped the one in the middle, unit vector. So in previous chapters, when you learned about the unit circle, what is the radius of the unit circle? Every time, all the time. It is always 1. Well, a unit vector is a vector that always has a magnitude of 1. And a unit vector is a very handy thing. I talked in the last section about a zero vector, a vector that has a magnitude of 0. Well, a vector that has a magnitude of 1 is very valuable, because that vector with a magnitude of 1 gives you a direction, and you can multiply it by other things. And because it has a magnitude of 1, when you multiply it, all it does is give you direction. It doesn't impact magnitude. Okay, so component form of a vector. You see you've got this crazy less than and greater than sign over here. It's really straightforward. The x part of the component, how far is it in the x direction that you go? So x2 minus x1. And then the second part of your component form is how far do you go in the y direction? y2 minus y1. So when you write the vector, it is a less than sign, a greater than sign. Not really, they're a little bit more straight up, but it's a bracket, an x value, comma, y value, and then this bracket. So it's an ordered pair that is a very quick and easy way to represent a vector. So let's look at it here. Component form of vector AB, you have an initial point and a terminal point. And remember, with vectors, let's go back. vectors have direction. So it always has to be x2 minus x1, y2 minus y1, where x2 and y2 are the terminal point, x1 and y1 are the initial point. So it's always terminal minus initial. So as you go here, it's going to be 1 minus 1 and 3 minus negative 3. Always works that way. 1 minus 1 is 0. 3 minus negative 3 is 6. So this is the way, let me go to a pen here. This is the way you would write a component form vector, bracket 0, 6. And the way you would say that is vector 0, 6. And what that means is the vector goes 0 in the x direction and 6 in the y direction. And this vector starts at 1, negative 3, goes to 1, 3. This vector represents starting at the origin, going 0 in the x direction and 6 in the y direction. So very straightforward. Okay, you give this one a shot. Remember, it has to be b minus a. I'll give you the answer in 3, 2, 1. Okay, so it's 9, 6, 5 minus negative 4. 5 plus 4 is 9. 3 minus negative 3 is 6. So this vector that goes from negative 4, negative 3 to 5, 3 goes 9 units in the x direction and 6 units in the y direction. Now, since you know how far you go in the x direction, you know how far you go in the y direction, to find the magnitude of the vector, two ways to think about it. You just use Pythagorean's theorem. This side squared plus this side squared is equal to the magnitude squared, which is what's represented right here. Or this is the distance formula that you learned in 6th or 7th grade. So very straightforward. Let's do an example. Find the magnitude of AB with an initial point A and a terminal point B. So the first thing you do is you find your component form. Actually, they're not going to do it this way. They just take x2, x1, so 1 minus 1. 1 minus 1, 3 minus negative 3. So it's 6. So if you were to write this in component form, it would be 0, 6. And that's really lousy handwriting. So 0, 6, and the magnitude of that would be 6 as well. So we're going to look at this in a couple of different ways. I'd like you to give this one a shot. Remember, it's b minus a. I give you the answer in 3, 2, 1. It's 7, and what works out really great, because the y value is negative 2, negative 2, the component form of this vector would be, I'll see if I can use some better handwriting here. In the y direction, negative 2 minus negative 2, that's 0. Negative 3 minus 4 is negative 7. So this vector goes 7 in the negative x direction and 0 in the y direction. So the magnitude is going to be 7. Okay, you remember adding vectors? How when you added one vector to another, you had to use the law of cosines and use the law of sines and make sure you drew them correctly and so forth. If you break your vectors down into component form, all you have to do is add the x's and add the y's, and you end up in the right place. Subtraction, you subtract b from a, and scalar multiplication, you just multiply your x and y values by whatever the scalar is. So let's do a quick example here. 2w plus y. Here's w, here's y. Let's step through this. 2 times w plus y. 2 times the vector 2, negative 5 is 4, negative 10. And you add that to 2, 0. 4 plus 2 is 6. Negative 10 plus 0 is negative 10. So your answer is 6, negative 10. Now, wasn't that much easier than trying to draw them out, find the magnitudes, find the angles, use the law of cosines, use the law of sines, and then find more angles like we did in the last section? I think you will like component form much better. It is much more straightforward, and when you get into physics next year with Mr. Schmidt, this is the way you're going to be adding vectors. So this is good to know. Okay, same thing with this one. 3y minus 2z. You take 3 times the vector y plus negative 2 times the vector z, multiply them through, add them together, and you get the vector 8, 8. Imagine if you were adding 4 or 5 vectors together. You would have to do the law of cosines and the law of sines 4 or 5 times. This is a much more straightforward way to add vectors. I'll let you have a shot at this one. Go ahead and pause the video, and when you get the answer, go ahead and unpause. Give you the answer in 3, 2, 1. If that's not the answer that you got, go ahead and rework the problem in groups to make sure that that's the answer that you get. And that's where you should end up. Okay, now finding a unit vector. In order to find a unit vector, whatever the vector is, it has a magnitude, right? Whatever the magnitude is, if you divide this vector by its magnitude, the magnitude is going to be 1. So the first thing you have to do is find the magnitude and then multiply the vector by 1 over the magnitude. So 1 over the magnitude times the vector. Because the vector has a magnitude, divide it by the magnitude, and you end up with a magnitude of 1. Sounds kind of crazy. Let's step through it. So the way you would write this is 1 over the magnitude vector 4, negative 2 times the vector 4, negative 2. The magnitude of 4, negative 2, it's 4 squared plus negative 2 squared square root. That is the Pythagorean theorem. So you can just apply the Pythagorean theorem, and because you know the x side is 4, the y side is negative 2, you can just go ahead and calculate that. So 1 over the square root of 20 times 4, negative 2. Well, square root of 20, you can simplify as the square root of 4 times the square root of 5, or 2 times the square root of 5. So let's do that. And now we need to multiply this number through the vector. So 4 times 1 over 2 square root of 5 is 2 over square root of 5. And this is negative 1 over square root of 5. And you can't leave radicals in the denominator this year. With great excitement, I will tell you in calculus, quite often you can leave the radical in the denominator. This is pre-calculus, so you can't do that. So rationalize the denominators. You have 2 square root of 5 over 5 and negative square root of 5 over 5. That is a unit vector in the same direction as 4, negative 2. Now, how can we verify that this is a unit vector? Well, let's find the magnitude. The magnitude is x squared plus y squared square rooted. So if you go through, take each term and square it. 2 square root of 5 over 5 is 4/5. Square root of 5, negative square root of 5 over 5 squared is 1/5. 4/5 plus 1/5 is 5/5 or 1. Square root of 1 is 1. So the magnitude of the unit vector is in fact 1. And also, when you have a unit vector, you normally use the notation of u to represent a unit vector. Okay, find the unit vector in the same direction as 5, negative 3. And I'll give you a minute to do that. Go ahead and pause the video. Okay, I'm going to give you the answer in 3, 2, 1. And what you should notice on this is 5 squared is 25. Negative 3 squared is 9. 25 plus 9 is 34. So since so square root of 34 is the magnitude, so it's 1 over the square root of 34 times this vector. And what you'll find when you do enough of these is whatever the magnitude is, you get square root of 34 divided by 34, square root of 34 divided by 34. Now, there are ways, if you simplify it or something like that, but as a general rule, that works out and is kind of straightforward. So unit vectors, a lot of people get concerned because they have to deal with radicals. And welcome to pre-calculus, where you have to do a lot of algebra. And if you think this is a lot of algebra, when you get into calculus, you'll do more. So practicing your algebra in and amongst your trigonometry in pre-calculus will prepare you very well for your calculus class. Okay, so writing a unit vector as a linear combination. Haven't introduced linear combinations yet, so let's go ahead and get started. You have an initial point and a terminal point. You're going to write it as vector ij, and I haven't introduced ij yet. We'll get to that as we go through all of this. So in component form, x2 minus x1, y2 minus y1, and it's 5, 9. And whether you're writing in component form or linear combination, it is the exact same vector, just a different way of writing it. So eventually we're going to get to the answer, but let me just show you that if you want to write, I'm going to change the pen color because I can. I'm going to go blue. So if you have the component form vector 5, 9, and you want to write this in linear combination, it is 5i plus 9j. So all you do is you take your 5, you put an I after it, take your 9, you put a j after it. There's a long history of why it's I, j, and if you go to 3 dimensions, it's k. This is not negative square root of 1i. This is I, j, and k used in some engineering applications, which is why it is in linear combinations. So we have our vector. It's in component form. Now it is in linear combination. So you can see as you look at these two that while it's a different form, it is the same vector. 5s are the same, 9s are the same. It's just to use brackets and parentheses as an ordered pair, or do you write it in IJ format? And sometimes some people will refer to linear combinations as the IJ format or the IJK format when you get into 3 dimensions. Okay, let's see if you can do this one. Go ahead and pause the video. I'll give you the answer in 3, 2, 1. Okay, so this is terminal point of negative 1 minus negative 4, which is plus 3, so you get 3. And then 5 minus 3 is 2. So that's how you would get that. Okay, now, if you are given a magnitude and direction, how do you turn that into component form? And I will caution you, draw the triangle. Make sure it's in the right quadrant, because you need to make sure that you end up in the right quadrant with your answer. So your vector v is going to be magnitude v cosine theta, magnitude v sine theta. And this works just because magnitude v cosine theta, that's the hypotenuse times cosine theta, is the adjacent. Magnitude times sine theta is the opposite. And I'll show you that on the next slide. You just plug in the magnitudes already given, angles given, just plug that in, and you will be required on the 30 and 45 degrees to know the values of sine and cosine without using your calculator. And then you simplify, and there you get your answer. So if you look at the triangle, the x value, the x side right here, is going to be the adjacent side. And the y side, can't draw a straight line. That's kind of a sine wave. The adjacent side, you would use sine. So sine of 60 degrees is opposite, should have said opposite, is opposite over hypotenuse. And cosine of 60 degrees is adjacent over hypotenuse. And that's where those equations come from. So if we go back to the equation that you need to use, magnitude cosine is x, magnitude sine is y, and you get that from this drawing a triangle with the vector here. Okay, give this one a shot. I'm going to give you the answer in 3, 2, 1. Okay, so the first thing to point out is if the angle is 30 degrees, you're going to be in the fourth quadrant, so x needs to be positive, y needs to be negative. So if x is positive, y is negative, it has to be either B or C. And because it's magnitude 12 in that direction, this would be way too long. So cosine of 300 degrees is 1/2. Sine of 300 degrees is negative square root of 3 over 2. You should either know that or know how to figure that out using the unit circle to answer this problem. Okay, now, if you're given the point, how do you find the magnitude and direction? In this case, you're just looking for direction to the nearest tenth of a degree. And because y is the opposite and 2 is the adjacent, it's just inverse tangent of 9 over 2, 77.5 degrees. So that is 77.5 degrees. Now, if you're asked to write it in some other form, you need to do that. And of course, you can find the magnitude. It's the square root of 2 squared plus 9 squared, if you need to do that as well. Didn't ask us to do that. Okay, direction of the angle R, -7, 2. Here's where it gets a little tricky, because you're going to do the inverse tangent of -2/7. Inverse tangent is going to give you an answer in the first or fourth quadrant on your calculator. You need an answer in the second quadrant because x is negative, y is positive. So when you plug into your calculator inverse tangent of -2 over 7, -15.9 degrees, you're in the fourth quadrant. To reflect the fourth quadrant into the second quadrant, add 180 degrees, and you end up at 164.1. So when I say add 180 degrees, it's 180 minus 15.9, but your angle was -15.9. So you just need to reflect from the fourth into the second quadrant. You should have done that back in chapter 5. This will just be a little bit of a refresher for how to do that. Always, 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 when you are doing inverse trig functions, make sure that your answer is in the correct quadrant. Inverse, sine, and tangent will always give you answers in the first and fourth quadrant. Inverse cosine will always give you an answer in first and second quadrant. You need to make sure that you reflect it into the correct quadrant if you need to, based on the problem you're given. Okay, now finding this angle, same thing, give it a shot. I'll give you the answer in 3, 2, 1. Okay, this is 104 degrees. Now, again, second quadrant, inverse tangent is going to give you an answer in the first and fourth quadrant. So when you do the inverse tangent of 4 over -1, that gives you an angle -75, -76, I guess -76 degrees. So you add that to 180 and you get 104. Okay, last example. And this is where you're really going to enjoy using component form, because you have a soccer player running and then kicking a ball. So running at 7 meters per second, kicking a ball at 30 meters per second at an angle of 10. So the first vector, the running vector, is 7, 0. That's very straightforward. The ball is 30 cosine 10, 30 sine 10, which gives you 29.5, 5.2. You just add that to 7, 0. So 7, 0 plus 30 cosine 10, 30 sine 10, you end up with 36.5, 5.2. Isn't that much easier than using the law of cosines and the law of sines to figure everything out? And breaking each vector down, you get your resultant. And if you need to find the magnitude, you just square x and y, take the square root of it, you get the magnitude. And to find the direction, you just do the inverse tangent. So wouldn't you rather break it down into component form using sine and cosine, add the x's, add the y's, square the x's and the y's, add them together, take the square root, and then do the inverse tangent of y over x. And you get your answers. I think it's a much more straightforward way. And we kind of had to go through the geometry way first so that you can understand what the vectors are doing. And then you go into this particular way of breaking it down. So component form, linear combination. You can write it in either format. They are exactly the same thing, just written in a different format. As a general rule, whatever format the question is in, that's the format the answer should be in. But if it doesn't specify, you can go with either one. And I'm going to let you have a shot at this one. Give you the answer in 3, 2, 1. And if you did not come up with this answer, go back and look at the previous example or look at example 8 in your book, because this is almost identical to example 8 in your book. And that is it for this section. Hopefully it was a little less confusing, a little less intense than the first section. And hopefully vectors will get easier for you as you work with them a little bit more. And putting them in the coordinate plane, for most people, makes more sense, and it helps them understand what we'll be doing in the next 3 sections of vectors in this chapter.